Hi everyone, so we're doing 27.4 today, the thermonuclear reactor. There's a question on here. Why is it important that nuclear physics is taught in the national curriculum? It's actually part of your specification, this question, so you need to try and think about what the answer might be. Learning objectives, be able to explain how a nuclear reactor works, be able to describe a thermonuclear reactor and explain how a nuclear reactor is controlled. This question, I'm not sure about what reasons you came up with, but you do need to know a reason for your specification. So the answer, and this is the exact answer that's given in the specification, is knowledge of the physics of nuclear energy allows society to use science to inform decision making. So for example, if you were deciding what political party you wanted to support and they had a manifesto that included some information about nuclear energy, you would be able to make informed decisions about that nuclear energy because you had the physics to and understand it. So this is the thermonuclear reactor. You might want to pause it here to draw a diagram. What you've got here is the reactor core. So this is the radioactive bit. And inside you have water or some other cool like some other fluid, and in here you've got your fuel rods. So these dark red ones are the fuel rods. In this diagram they're using water as a moderator. We'll talk about a moderator later, and as a coolant. And then here you've got control rods. But in other nuclear reactors, you'll have moderator rods here too, okay, as well as control rods. We'll learn what these do shortly, and the fuel rods are the uranium fuel rods. We then have so as water moves through here, it gets warmed up by the nuclear reaction here. Warm water travels around, it's pressurized, and here we've got heat exchange. So what you do is you have cold water come in at the bottom, completely separate, and the warm water that's been through the thermonuclear reactor will then heat up the water in here, and that will go out and to the turbines and a steam, and turn the turbine to create electricity, and then it'll come back round again. Okay, keep going round. These two are separated from each other, so this water here that turns to steam is not radioactive. It doesn't have radioactive particles in, but this water could. So the fuel rods are evenly spaced in the reactor core so that you get a nice even reaction. And the core also contains coolant and control rods, but it might also contain moderator rods as well. The reactor is connected to a heat exchanger by steel rods, and a pump is used to force the coolant through the reactor core where it is heated, and through the heat exchanger where it is used to create steam to drive the turbines. This pressurizer here pushes, and the pump pushes all of this round and round and round and round and round. The fuel rods contain enriched uranium. So if you look at uranium-238-92, it's 97 to 98% of it is non-fissionable. So only 2% of it, 2 to 3% of it is actually fissionable. Natural uranium that you just dig up only contains about 1% fissionable material. So you need to enrich it to make it fissionable. So enriching it involves bombarding it with neutrons. Okay, so you're turning it you get more energy from this enriched uranium than you would normal uranium. And in fact, you can enrich it even more, so you can enrich it, up to 90% enriched uranium. But 90% enriched uranium would cost a lot of money to enrich it because you have to, and you're bombarding it with neutrons, and so that costs a lot of money. So the money you get from the electricity you make wouldn't cover the cost. But you can enrich uranium for weapons, so you can have enriched uranium and plutonium for weapons, and so the cost of doing that is mitigated by the fact that you want a weapon that can kill lots of people, and so you don't really care about the cost. But yeah, you have to enrich, because natural uranium is only about 1%. So they enrich it. So this 2 to 3% gives you enough of a profit margin from your electricity for the cost of buying the enriched uranium. Now the control rods absorb neutrons, so the depth is controlled, so only one fission event is allowed to occur following a previous fission event. So a fission event will produce 2 to 3 neutrons, as we learned last lesson. So you need to absorb 1 or 2 of them, so that you're only left with 1 fission event. So the control rod's job is to absorb neutrons. They're usually made from boron, and the fission, the moderator has a different job. So the fission neutrons, when they're created, they're too fast. So the likelihood that they're going to go on to split a uranium nucleus is low. So they need to be slowed down, which increases the chance that they're going to split a uranium nucleus. So in order to slow down and cause another fission event, you need something called a moderator. And the moderator surrounds the fuel rods. So you might have moderators in here as rods, or you might have them as, in this case, they're using water. The moderator rods themselves are usually made from graphite, or put carbon there, I mean carbon, okay? What happens is the neutrons collide with the moderator atoms and lose their kinetic energy, therefore slowing them down. So for a chain reaction to occur, the mass of the fissionable material must be greater than a critical mass. This is because some of the fission neutrons escape, and if the mass is less than the critical mass, then there's not enough fission neutrons left to cause the chain reaction. So there's quite a balance there. What are the safety features of a nuclear reactor then? So the reactor core itself is made of really thick metal. It withstands high pressure, high temperature, and shields against beta and some gamma radiation. And obviously alpha as well. The core will be in a building with massive thick concrete walls to absorb escaped neutrons and gamma photons. There's an emergency shutdown system where the control rods are fully inserted to stop fission completely. This is what didn't happen at Chernobyl. They couldn't get the control rods in properly, and so the emergency shutdown system didn't work, and therefore the chain reaction got out of control and it exploded. You also have remote handling devices, so they can remove the fuel rods. You don't want to send someone in to take the fuel rods out and swap them for new ones. So spent fuel rods are really radioactive because the daughter nuclei that are created are going through several stages of radioactive decay. That also means they're very hot too, so they're hot and really radioactive. So what do you do with them? So the high level nuclear waste is the most active, e.g. those spent fuel rods. And they're removed by remote control, and they're stored underwater in a cooling pond up to a year as they release heat by radioactive decay. Now don't call that cooling pond a swimming pool. It looks like a swimming pool. It's a beautiful blue colour if you see some images of them, but it is called a cooling pond. You would not swim in it. And then they're transported to Thorpe, which is the processing plant, the nuclear waste processing plant at Sellafield, and Sellafield's in the image in the virtual classroom. Unused uranium and plutonium can be removed from the fuel rods at the processing centre, and then they can be reinserted into another fuel rod, so they're stored in some special concealed containers. The rest of the material is sealed up in a container and dug into deep, deep trenches covered in concrete and left for centuries. Some countries, that's supposed to say, sorry. So some countries mix high-level waste with glass, because when it's mixed with glass, if you think of glass, if you break it, it separates into solid pieces that can be swept up. So you put it into glass. It's called vitralization, I think. So yeah, they mix it with glass and then store that glass deep underground, so that if it was to break, it wouldn't actually decompose or anything. It would just stay within the glass. The intermediate level waste, so low activity radioactive materials, are sealed in drums and then encased in concrete. They're stored in specially constructed buildings with reinforced walls. Then the low level waste, so lab equipment, PPE, they're sealed in metal drums and buried in the large trenches. So that's the end of the information. On the PowerPoint, I'll add the questions. So I want you to have a go at the questions and then mark them. I'll answer the questions in a video, so you can watch the video to get the answers. There's a couple of other videos in the virtual classroom that I want you to watch as well about transporting radioactive material. Thank you.